Okay, good morning everyone. I think that's perfect weather for a bit of operations research and queuing theory. Are there some questions about last exercises, lectures and so on? Okay, so I think I don't get it here. Okay, I will carry it. Okay, so just short recap where we finished last time with an example of a scheduling model where we try to get an optimal schedule for outpatient problem. So the problem is we had that already, and the question is now, these are the parameters we know, so this is what we give the model to optimize. We know that we are open between 8 and 12, let's say, and our length of time interval is always 1 hour, for instance, D, and we have to schedule whatever, 12 patients also. And the service duration, so the time is exponentially distributed with parameter mu. This is what we know. And what we want to find out, to determine, is the number of patients scheduled at the start of the interval. So let's assume we have 4 time intervals, from 8 till 9, 9, 10, 10, 11, 11, 12. Then what we want to know, and this is the solution of this optimization model, is how many patients to schedule in these particular time slots. 5 at the beginning, then 3, then 2, and so on. Okay, to find the optimal solution such that we can minimize the overall costs, which consists of the waiting time, the average waiting time W, the idle time, and the overtime or the lateness. Okay, weighted by alpha L, alpha I, and alpha W respectively. Okay, so this is what we want to understand. We want to minimize the costs for waiting, idle, and overtime, and to get this optimal number of scheduled patients per time interval. Okay, so how to which time slot to assign these patients? Okay, so the optimization model was such that we want to minimize the cost, but under the restriction that all of our patients, 12 patients let's say, are treated on this particular day or within the time horizon, capital T. Okay, and we had some variable blocks, so we can decide how many patients will be treated within this time intervals, but the time intervals are always fixed. So for instance, 1 hour, 8 till 9, 9 till 10, and so on. Okay, there's no classification on the patients. We don't differentiate between them, and we also don't have any kind of adjustment rules. We also don't consider no-shows, for instance. Okay, no walk-ins, no unpunctual patients or emergency patients. It's simply on first-come, first-serve basis. Okay, in the exercise we will also include the no-shows, but here we exclude that for simplicity. And in order to minimize this objective function, we have first of all to understand how to determine waiting times, idle times, and overtimes. And for these time types, we have to understand first of all what is a Poisson process. Someone ever heard about Poisson process, Poisson distributions in whatever, queuing theory, statistics? Ever heard of? Just heard. I don't want a definition, just that I want to know if you ever heard Poisson distribution. Okay, thanks. So here we have that the interval time, so between the patients, are exponentially distributed with parameter mu, if and only if the number of time, oh wait, I forgot to use the laser pointer. So only if the time of interval endpoints in a particular length of time follows a Poisson distribution. Okay, so basically a Poisson distribution models the number of events in a fixed interval of time. So if, for instance, the occurrence of patients within 1 hour, and the exponential distribution models the time between successive events in a in a Poisson process. Okay, so the time between the occurrence of patients. So, for instance, if we, I don't know, if on average you expect patients every 3 minutes to come in, then we would obviously expect 3 patients within 9 minutes. Okay, and this is exactly the duality between the distribution, the Poisson distribution, and the exponential distribution. So, in the exponential distribution, you ask for the time between the patients. Okay, so how much time has passed till the next patient is coming or can be treated. And in the Poisson distribution, you want to know how many patients can be treated within 1 hour, for instance, in a given time span. Okay? Okay, so the official definition is for the Poisson distribution is the probability that exactly patients are coming in within a particular time frame, and the random variable y is exponentially distributed. This is the time between patients, and the exponential distribution is memoryless, which means that the probability of an event occurring in the next moment is the same regardless of how much time has already passed without the event. So, simple example, if you expect on average a patient every 30 minutes and no patient has arrived, then the probability that the next one is coming in 30 minutes is the same. So it doesn't matter if a patient has arrived, the system forgets that you already waited for 30 minutes, okay? So if no patients have arrived in the last 30 minutes, the expected time for the next patient is still 30 minutes, okay? This is an important property for the next computation things. Questions so far to this memoryless? Okay. It's simply that it forgets that you already waited, okay? It is independent of how long you waited already. Okay. So that means the differentiation between the Poisson distribution and exponential distribution. So here you know you have 1 hour, and the occurrence of patients is Poisson distributed. That means we have 2 occurrence of patients in the first hour and 3 patients within the next hour. Okay, so this is the number of patients within a given time period, and the y variables are exponentially distributed. So this is the time between the patients, either that they occur or that they are treated. And you can see here that here this is shorter, this is longer, but overall it's exponentially distributed. So the time between the patient arrivals. Here you ask for the numbers, here you ask for the time, basically. This is the only difference, and also the duality between both distribution types. Okay. So if you have already a schedule, and let's say you have 5 in the morning from 8 till 9, then 3 from 9 till 10, maybe we can write it down. I can try to check if this works. Okay, I don't know. Okay, I need my finger. That's bad. Okay, so let's assume. Okay. This is here T. So T1 is from, let's say, 1 till 8 till 9, and oh my goodness. Sorry, I don't have a pen. So and this is the second time period. This is sorry for that. Back. Okay. I try again. Okay, so this is at 8. And this is at 9. Oh man. You have to wait simply for ages then. So, and in the beginning, we assign 5 patients, and at 9, we assign 3 patients. Okay, so assume we have that already. So, sorry for this bad drawing. And what we want to know now is the probability that J patients are in the queue either before or after the arrival at a particular time interval. So at 8 or 9 or 10, whatever. Okay, so at T0, of course, nobody is scheduled. Therefore, the probability that shortly before 8, so 7:59, there are 0 patients is 100%. Okay, that's obvious. Okay, then the probability that shortly after T, there are J patients in the system, so that at 9:01, there are J patients less than XT, so we assign 3 patients, and the probability that only 2 patients are in the system is 0. Because we assume that if we assign, we exclude no-shows. That means if we assign 3 patients at 9, then all 3 patients will arrive exactly at 9. So at 9:01, there will be at least 3 patients still in the system. And that means to have less patients is the probability is 0. Okay. And here, to have J patients, which is at least XT, this is exactly the probability that shortly before T, so 8:59, there are still J patients from the previous time slot minus our new arrivals. Okay? Okay, so 9:01 is the probability that shortly before time T we had J minus XT patients in the systems. Okay, so the new number of patients shortly after time T, so 9:01, equals the previous patients who are still there, who couldn't be treated within this 1 hour. Okay. I would like to write an example, but I'm afraid that you won't read it. Okay, maybe. I try. If not, then it doesn't work. Okay. So for instance, to know that the probability for time period 2, which is at 9, this should be a plus. To have, oh my goodness, this is a plus, okay? So the probability to have at 9:01 4 patients, this is a 4, is the same as having the probability that shortly before time period 2 started, so at 8:59, there were 4 minus 3, so 1 patient is still there from the previous time slot. Okay, so 5. Wait, wait a minute. I need a pointer again. So we assigned 5 patients at 8. And the probability to have here 4 patients in the second time slot is simply the probability that there is still 1 patient in the system. So 4 patients were treated between 8 and 9, and 1 patient is still there and is waiting for the treatment. Okay. Is that okay? Clear? Okay. Then we also need additional probabilities. This is all needed for defining the waiting time, idle time, and overtime for this objective function you remember at the beginning. So for this purpose, we need, first of all, the probability that exactly patients have been treated. Okay, this is given using the notation A. Okay, And the probability that at least I patients have been finished in this time period is simply 1 minus the counter probability that less than 5 patients are finished, for instance. Okay, so from 0 up to 5 minus 1, so up to 4 patients are finished. Okay, so this is exactly that I patients are finished. This is at least I patients can be finished. These are the probabilities. And we say that the service times are exponentially distributed, again with parameter mu. And although idle time can occur because we don't have so many patients, we are open between 8 and 9, between 8 and 12, and we have to, have to treat 9 patients, and the last one is leaving at 11:30, we have still 30 minutes idle time. Although this is the case, we assume still that this is a Poisson process. So the key idea is that although idle time may occur, because we have a lack of patients, the system still functions as a Poisson process. Okay? So we can assume all the properties and we can use all the properties of a Poisson distribution. Okay, so we had the probabilities that patients are still in the system, so before the time slot begins. And now we want to know the probabilities that shortly after the time slot has started, that J patients are in the system. Okay, so shortly after 9:01, what is the probability to have exactly J patients in the system? And this is that the probability that J is simply the sum of all cases where we have the probability of having I patients in the system. I is at least J up to N, multiplied by the probability that I minus J patients have been treated and can leave the system. Okay. Okay. And on the other hand, to have no one in the system shortly after a time period has started, okay, 9:01 or 10:01, whatever, this is the probability that at time t there were I, again I, which is up to N patients times the probability that at least I patients have been treated and could leave the system. Okay. Okay. So before we had the probability that still J patients are in the system from the previous time slot, and here is what is the probability that shortly after the time slot has started we have exactly J or 0 patients in the system. Okay. And it depends obviously on the probability of that exactly I minus J or at least I patients could be treated. Okay, so how many have left the system? Okay. And now with these probabilities and this assumption of Poisson distribution, exponential distribution, and so on, we can now determine the mean waiting time. So this is the first component of our objective function. So again, we assume exponentially distributed random variables with parameter mu and the mean 1 divided by mu. So if you have 3 patients within 1 hour, so if you can treat 3 patients within 1 hour, what is mu then? So what is my service rate, mu? 3 patients within 1 hour. And as long as you think, I drink. So what is my service rate if I can treat 3 patients within 60 minutes? Sorry? This is the service time. This is 1 divided by mu. But you're right. So what's then mu? It's simply the reciprocal. So 1 divided by 3 divided by, sorry, I won't explain that. So, but this 20 is 1 divided by mu, exactly. So, but what is the service rate mu? So if 1 divided by mu is 20 minutes, this is the service time. What is the service rate mu? Is that tricky? Yeah. It's 0.05. It's 1 over divided by 20. Okay. Yeah. Exactly. So that means if a patient finds K patients in the system in front of them, okay, then obviously the waiting time is K divided by mu. So each of these, let's assume we have, I don't know, 2 patients in front of me, and each of them requires 20 minutes of treatment time, then I know I have to wait 40 minutes. Okay. And of those who are not that lucky, they obviously will wait longer because it's on average, right? Okay. And there are some lucky ones who will wait less than that. Okay, and we assume that patients arrive in groups just before the start of their time interval. And the question is, what is the probability, or let's say the waiting time for the each patient of this particular group? So we said 5 patients were assigned from 8 till 9, and at 9 new arrivals, 3 patients. Okay, so I'm at 9, I'm assigned to the 9 o'clock slot. So I see when I arrive here, I'm let's say I'm the first one in my group of these 3 patients, and I see J patients still in front of me. Okay, so from these 5, I still see 4 in front of me, multiplied by the probability. So how likely is it that I see 4 patients still waiting? Okay, plus I have to wait. If I'm the first one, I simply have to wait till J patients in front of me I treated. If I'm the second in my group, then obviously I have to wait till J patients are treated plus the 1 from my own group. So 2 minus 1, 1 patient is in front of me, and I have to wait J plus 1, and each of these patients require 20 minutes of service time. Okay. So that means overall we can now finally define the waiting time for the objective function, which is basically over all time slots, over all assigned patients, and over all patients at all for this entire day, for instance. Okay, and as said before, so J patients are still in the system plus the new arrivals multiplied by the probability that shortly before the new arrivals are coming in, we have still J patients in the system. Okay, and each of these patients, they require 20 minutes of service time. Okay, and because we want to have the mean, we have to divide it by n, the number of all patients that have to be treated. Okay, so for this we have the first component of the objective function. Then the next one was idle time. Okay, how to define idle time. For this we have to first of all determine the make span. Make span is simply the total time required to finish all services. So the last patient is leaving at 11:30. That means our make span is 11:30. Okay, and for this we have to define a t tilde, which is the last time interval during which a service can be started. So the time t where we still accept patients. Okay, if we are open from 8 till 12, then we know at 11 we will still accept patients and will still assign patients. So our t tilde would be 3, right? What did I say? At 11, right? So 4. So t would be 4. If we think we have open till 12, so the last time period where we accept patients is T4, okay, at 11 o'clock. Okay, so and here the first term just represents the time until the beginning of the last interval T tilde. Okay, so how much time basically has elapsed until last interval started? We said T tilde is 4 minus 1, so 3, and we assume a 1 hour duration, so 3 hours already passed. And the second term, it simply this calculates the mean remaining service time of all patients still in the system after the T tilde, so after the last interval has started. Okay, so this is basically the expected remaining service time of the J patients still in the system, okay, shortly after 11 o'clock. Okay, so that means the mean makespan is the sum, okay, of the elapsed time until the last service interval started, so 3 hours have already passed, plus the expected remaining service time of the patient still in the system, okay? So this is the expected one, not the actual one, okay? But still, this is the expected makespan we have to use to determine actually the idle time. So this is pretty intuitively reasonable. Mean idle time is simply the makespan, so the last patient left at 11:30, whatever, minus the mean total service time, which is actually the actual workload, and this is the n divided by mu. Okay, so this is the workload we have. Okay, and that means we have to subtract from the makespan, okay, the workload we have. Okay, so the service time for all patients. Okay, so if let's say the last patient left at 4 o'clock, after 4 hours, I mean, so 240 minutes. The question is, how long was the doctor busy? So he treated, let's say, 10 patients. Everyone needed 20 minutes. So 240, the last one left after 240 minutes, minus overall he needed 200 minutes of service time. So we have an idle time of 40 minutes. Okay, 240 minus 200. We have 40 minutes he had nothing to do. Okay. Questions so far? Okay. Okay, so this is the second component of the objective function, and now we need the third one. So the mean tardiness, lateness, or here overtime. So the question is, who is still there after 4 hours? Who's still in the system after we officially closed at 12 a.m.? PM. And the tardiness is determined by the patients in the queue at the end of the last time block. Okay, so simply, what is the probability that J patients are still in the system shortly after 12, so 12:01, something like this. And all of them, these J patients, all of them require 20 minutes of service time. Okay. Okay, so now we have all these components: waiting time, idle time, and tardiness, lateness, overtime. And now we could potentially solve the optimization model analytically, however, or to optimality. But the problem is that we have too many number of possible schedules. So we have n plus t minus 1 over n possible schedules that should be tested before we can say which one is the optimal one with respect to the costs, okay, the time costs. Okay, this is especially for real-time and real problems. This is simply too time-consuming. Okay, we need too much time to solve that, so therefore we need a faster algorithm. And maybe you're also familiar with heuristics. Someone ever heard about local search algorithm, local search heuristic? In your bachelor's or no one? Okay, but heuristics, I think it's something. Okay. So with the basic idea is we start with a feasible solution. Let's say we have 4 time slots from 8 till 12, and we have to treat, let's say, 12 patients. So we assign 3 patients and for each hour. Okay, this is a feasible solution. It's not necessarily an optimal one, who knows, but first of all, it's feasible. Okay, we assign 3 patients to each of these 4 time slots. And then iteratively, we try to improve the solution by searching in the neighborhoods. Okay, so what is the neighborhood? This will come in a second. And then we will find a local minimum. And in general, what we know from heuristics, that they find often local minimas, but not the global ones. So I will try to draw it again. So if you have, let's assume some kind of dysfunction, then heuristic could find this optimum, this local one, but not, and this would be the global one, but not this one. Okay, so in general, heuristics cannot guarantee the global optimum. However, for this particular case, the authors could show that this is also a global minimum. Okay. So this is why we cannot solve it using an optimization solver, state-of-the-art solver, Gurobi, Cplex, whatever. Simply too many possibilities. You can, if you see the time slots as basket, you have too many possibilities to assign the patients around. Okay, because it's drawing with putting back without considering the order, because we don't differentiate between the patients. Okay, and this is why you have this huge number of possibilities. Okay, so what is a neighborhood? If we consider I need a pointer again. Okay, so if you consider a single shift move, okay, so for instance, I would like to draw, but let's try. So as I said, we have a feasible solution, which is 3 and 3. Okay, so we treat 12 patients and we assign 3 patients per time slot, and a single move means we move 1 patient to this one or 1 to this one and then back. So we move 1 patient at one time. Okay, and a neighborhood is the combination of all single shifts. Okay, so we have an X. Okay, this is our X. This is our first feasible schedule. Okay, so this is our feasible schedule. And now we try to find the neighborhoods where we move only 1 patient per slot. So U1 means we move from the first time slot to the last one. U2 means we move the second to the first one. U3, we move the third, the patient from the third slot to the second one, and so on, up to all these, in our case, 4 time slots covered. And so we have many vectors, and capital V is the set of all these shift vectors. Okay, all these vectors are saved here. Okay, and then the neighborhood of a schedule is all these vectors. So X, so our feasible solution, plus all these single shifts given here. Okay, and which is important is that the sum of all this is at least 0, because otherwise we would assign negative patients to a slot. Okay, this has to be avoided, and this we have to consider in our local search algorithm. Okay, so if we know what the neighborhood is, then we can start with a schedule. I just showed you a feasible one, and then we choose a subset of V. So we choose, let's say, the first 3 vectors, and then we check the computation, the costs for this particular shift. Okay, so what are the sum of all the times, so waiting times like idle time plus overtime, with the new schedule Y, and if this is less, if the costs are less than for the original schedule, we replace the schedule, okay, and start with this one again. So again, we choose a subset of all vectors, and we check if we can reduce the times. Okay, if you can reduce the objective function, till we have the optimal schedule with a minimum of waiting time plus idle time plus overtime. Okay. And we will have, because this rather theoretical approach, we will see in the exercise with real numbers how it goes. Okay, and the proof that this is really a global optimum is some pretty technical one, and it uses some kind of multimodularity, which is a particular type of convexity of the objective function. Okay, and they could show that their objective function has this particular type of convexity, and therefore they could show that this is a global minimum they found. Okay, but in general, heuristics are not providing the global optimum. Okay, so let's have a look on a numerical example. So we have a medical practice from 8 till 12 as before, and we have 48 time intervals. Each has 5 minutes. Okay, so capital T is 48 time intervals, and our time length is always 5 minutes. And the service time, so the treatment time, is on average 20 minutes. This is 1 divided by mu. Exactly, and that means if we have to treat 10 patients, okay, so the workload itself is 10 multiplied by 20, so we have 200 minutes of workload, okay, which is less than this time span of between 8 and 12, so we have actually 240 minutes that patients can be treated. So in real life, often we would assign more patients because we assume no-shows and so on, okay? But for this numerical example, we have less workload than opening hours. Okay, and we also consider for the numerical test at least a no-show rate of 10%. So with a probability of 10%, a patient might not occur, okay? Okay. So this is the basis for the numerical test, and what they've done, so the authors, they assumed different weightings. So for the overtime, they assigned 1, for the idle time 0.2, and for the waiting time 0.5, and then played around with that. But these are the basic parameters. And so that means they would like to avoid overtime, which is not very surprising because the study is from Netherlands and they don't like to work more than necessary. In Germany, it seems to be a joke, but it's indeed like that. And in Germany, they work rather overtime simply because of money aspects. Okay, so but this is a Netherlands study taken from real clinic over there. Okay, so if we play around with the weights for the waiting time. So first of all, we don't punish waiting time so much, so we accept that patients have to wait longer, and then we go up till 10. So what is done in general is that we try to standardize so that the weights overall, the sum of all weights is 1. But it's not necessary, it's simply for computation reasons. You can also use this one because what you need is the relative difference between between the weights. Okay, so it's not necessary to standardize it. Okay, so then that means that at the beginning they don't punish waiting time that much, and this goes up till 10. So where we try to avoid that patients have to wait too long. So what do you see here? So what would you say? What can you observe if you look at this? If we increase the weights for waiting time, something happens with the schedule, right? So we have open from 8 till 12, and all these black squares are simply patients coming in. What do you observe here if we increase the weights for waiting time? So if we want to avoid waiting times, what is different between the last and the first row? What would you say? Mm-hmm. Exactly. Exactly. So this is absolutely true. We see here that the spread is much wider than over here. Exactly. So that means if we want to avoid waiting time, then we simply spread out the patients, and the last one is coming really at 12. Okay, so shortly before 12. So if we want to avoid that patients have to wait, okay? That means that the doctor will wait, rather. Yeah, please. Sorry. Nine. 1, 2, 3. Do you see the 2 at the beginning? I don't know if you can see that. By the way, does it remind you, some of you? Of what does it remind you? This that we assign at the beginning 2 patients. If we use the a weighting of 0.5. So do you remember? If we assign 2 patients at the beginning of the schedule, what was it? Mm-hmm. Exactly. So we want to try to, if there are no-shows, to avoid that we have waiting or idle times, right? So this could remind you of this Bailey-Welsh rule we had last lecture. Okay, so let's summarize basically. So first of all, if the bigger the weight, okay, then the patients are spread out more than to the end of the schedule. Yeah, you would also expect that, right? If you want to avoid that patients have to wait, you would put some buffer in between, okay, so that you rather wait. And here at the beginning, this is to assign 2 patients in the beginning. It's rather this Bailey-Welsh rule, where you try to have to avoid idle times if there's some kind of no-show. And what is also what can also be observed is that in all these cases, the time between the appointments increases in the beginning and at the end, and decreases in the middle. So this is so-called the dome-shaped form. So the inter-arrival times are shorter at the beginning and at the end, but longer in the middle. Okay, this is also observed in practice. That, yeah, please. Yeah, then so one of them has to wait. till the doctor is done, and this is on this first come first serve basis. So he was first. He will wait till the first patient leaves the system, and then he's treated. And everyone else may be either even if they have an appointment, they have to wait, okay, in the waiting room. So everything shifts to the end. Yeah. Exactly. Yeah. Exactly. Yeah. Okay. Further questions? Okay. Then the problem was that the computation time is still 12 hours. So if you want to have a schedule for the next day, this is not possible because you have to wait till the results are done one day, okay? So this is basically rather on let's say for the next week, for the upcoming months and so on, then you can assign these schedules, but not on a short-term basis. And what is often done is that you collect the appointments, the requests, and then till some kind of cutoff day and cutoff time, and then you decide based on the demand for next Monday or something like this that you would like to have 3 patients in the morning, so from 8 till 9, then 5 patients from 9 till 10, and so on. So you don't assign the patient names or the particular patient and the illness. You simply decide how many patients to assign to a particular time slot, okay? And then someone who's picking up the phone, getting in a request, they know then, okay, I can still assign 3 patients for this particular time slot. Okay, so they know the capacity, okay? And if less patients are calling, then our time slot is not filled, okay, which is fine. But this is what is used for planning, okay? That I know if they are calling me, then I can assign them to a particular time slot, okay? Because I know I'm free to assign 5 patients in the morning, okay? And if they're calling, I know, okay, it fits. Okay, so this is the basic idea of this entire optimization model. So how many patients to assign to which time slot. Okay, so this is simply the summary. Bigger waiting time, then they are spread out. If we have this small weighting of 0.5, then this is close to the Bailey-Welsh rule, and then just explain the dome shape, okay, where the arrival are increased and decreased, okay, between the arrivals. Okay, so if we change a bit, okay, and we compare this optimal schedule based on this optimization model, and we compare that with more conservative, more, let's say, naive schedules, in particular with the individual ones and the Bailey-Welsh rule, which are very used in practice, okay? So this is nothing unusual to find these kind of schedule rules in practice. So can you remember what the individual schedule rule was? What does individual means? We have this block size. We have the variable ones. This is what we just seen with the optimization model. We assign 5 at the beginning, 3 in the second one, and so on and so on. What is individual one? How many can come per time slot in the individual rule? You can check your slides. Last time we had that. What does individual means? I mean, just intuitively, maybe. Exactly. So we have one patient per time slot, and Bailey-Welsh is the same basically, but with the exception that 2 are at the beginning, and then individual patients, 1 patient per time slot is coming. So we have 4-hour day, 10 patients. That means each block is 24 minutes. Okay, so we have 240 minutes overall. And if we have to treat 10 patients, then and we want to have an individual rule, so every patient is coming to their own block, then each block consists of 24 minutes. Okay, and every after 24 minutes, 1 patient is assigned. Okay, so that means we compare this one with the individual and the Bailey-Welsh rule. And you can see here that if you increase the waiting for the waiting time, then you can see that the mean waiting time obviously decreases. Okay, so at one point the individual and Bailey-Welsh rule are worse. If you consider the idle time, you can see if you increase the wait, then also the idle times increase, obviously. Okay, if you see that one, so the last row where you have to wait for the patients to arrive, and longer inter-arrival times, then obviously the doctor will rather wait longer, okay, for the next patient to arrive. Therefore, obviously the idle times increase with increasing waiting. And this is close to tardiness, obviously. So if you have to wait longer for the next patient to come, then obviously the overtime that you wait and have to work longer increases also. Because again, if you have a look here, so the last patient's coming at 11:55, then obviously the probability that you will work after 12, although we are closing at 12, is pretty high, okay? And therefore you can see that overtime increases, okay? But overall, so if you check the objective value, so the sum of all these waiting time, idle time, plus tardiness, you can see here that this is always better than the individual and the Bailey-Welsh rule. Maybe except this one, this is very close to the Bailey-Welsh rule. Okay, so for a waiting of 2, Bailey-Welsh and the optimization model will give you very similar objective function values. Okay. Okay, so if we play around with the parameters, what will change with the objective values, what will change with the schedules? We keep the workload, the workload is still the same, so we remember the workload was n divided by, so workload was n divided by mu. Okay, sorry, this is a mu, and we know beta is 1 divided by mu. Oh, okay, so this is so basically this is here the workload, and we also consider no-shows. That means we have a 10% probability that the patients won't show up. So this means we have a 100 minute of workload. So this is the same when we play around with parameters, and we have chosen, or the authors have chosen, a weighting of 2 because this was close to the Bailey-Welsh rule. Okay, so the objective functions are very close, and then they changed 2 parameters at the same time, rho and beta, n and beta, and n and rho. Okay, so if we play around with the rho, if we increase the probability that patients won't show up, okay, then obviously we have less, then we have also a beta that increases, and we can see here that the objective value, the overall objective value, increases also because of uncertainty. Okay. Okay, so the higher the level of uncertainty, the more we have to deal with worse objective function. Mainly because also the idle times increases, the waiting time increases, but also tardiness increases. Okay. So uncertainties, yeah, please. Yeah, the objective value is the sum of all these time types, okay, weighted by alpha. Okay. So the higher the uncertainty, the worse our objective function value is. Okay, then what if we change n and beta? So if we assume that we have more patients to treat, 8, 10, 16, and so on, and beta decreases, okay, then you can see that the objective value decreases, okay, and because we have reduced uncertainty over here, okay, and all mean waiting time, idle time, tardiness all become smaller, okay, in this case where you increase n and decrease beta. Okay, so if you somehow be able to decrease your treatment times, okay, maybe due to technology, routine, whatever. Okay, if you are able to reduce beta, then you can treat more patients, okay, and then you can reduce all these time types, and you can improve your objective value. Okay, and then you can also play around with n and also rho. So if rho becomes larger, we have higher no-show rates, and we have more patients to treat. This is the same as before. We have a higher uncertainty, and again, our objective value deteriorates, increases, which is worse. Okay. So uncertainties or variability in the system is often make it worse. Okay, especially for the planning. Okay, so the critic is that it's only approximately exponential distributed service durations. The same duration distribution is assumed for all patients, so we don't differentiate between the patients or the urgency or the complications of a patient illness. And what is also could be seen as a critic is that you tell the system or you tell the model the length of your T, D, and also the number of your patients. But often you might be interested, how many patients should I accept to have an optimal process? Okay, how long should my opening hours be to have an optimal schedule? Okay, so for this particular model, these are parameters that are given. So you have T, N, and D. But as I said, often you are rather interested in these parameters that should be also decision variables instead of parameters. Okay, and of course there's no consideration of walk-ins, emergencies, or over-punctual patients. Okay, there have been a practical seminar where they tried to extend this model by using time-dependent no-show rates. So not only no-shows, but also time-dependent. So if we assume in the morning the probability is higher if we have no-shows than during lunchtime or something like this. And what they found out is that here you see that you have the same schedule if you don't consider no-shows or if you have really small time-dependent no-shows. So this is the schedule for this case. If you increase the probability of no-shows to 10%, then this break shifts a little bit to the end. And if you increase the no-shows even higher to 30%, then you don't see a gap. But overall, there's small influence on the schedule itself. And to the right, you see the comparison of the objective values. If you don't consider no-shows, 10% no-shows, light blue, and in the case of black, it's 30% of no-shows. So this is the overall objective function value. Okay. If you consider the black case, if you have 30% of no-shows, you can see here that the waiting time is pretty small. overtime is almost neglectable, and you have a high or long idle times. Why do you still have such a small overall objective value? What do you think? Why is it that although this number is pretty high, you still end up with a small objective function value? How can that be? Yeah. And the more importance is shown by? Absolutely right, yeah. Exactly. So, the overtime is one, the waiting time is one, but the idle time has a relatively low importance weight. Okay, so it's doesn't have such an influence on the objective value. Okay, and this is why we have such a small objective value function at the end. Okay. Okay. So sometimes let's maybe finish with the appointment part, where you could, if you are a clinic, if you are a physician, if you are some kind of a department in a hospital, then often, and this is the majority of the cases, where you can assign appointments. Okay, that means you can better plan in the future. You can assign patients for the next 2 weeks, month, and so on. But what if you have a walk-in clinic? What if you have an emergency department where you cannot assign appointments? So how can you plan and how can you optimize your processes if you are facing a high level of uncertainty? And this is used in walk-in policies, and we will use queuing theory here. So just a recap, we remember that walk-in policies applies if they simply arrive randomly without any appointment, maybe because they have an emergency or because some clinics, they don't like it. And as soon as the capacity is filled, so we have one doctor and the doctor is treating one patient, the next one coming has to wait, okay? And a queue is forming then, obviously, so these are waiting lines. As I said, we can have it in emergency departments, or some doctors prefer to allow rather walk-ins instead of appointments, because they know the probability of no-shows are pretty high, the probability of emergency cases occurring are so high, it makes no sense to use an appointment schedule. We simply have a walk-in a clinic. Okay, what does it mean? Patients, as I said, arrive randomly, and then as soon as the server is blocked, so the doctor is treating a patient, there is some kind of queue forming in the waiting room. Okay, and as soon as they are done, then patients are leaving the system again. Okay, so this is pretty straightforward. And the reasons why we observe queues are, as I said, obviously the uncertainties. We have variable arrival times, so we not really know when the patients will arrive. We have variable examination times. Sometimes one patient requires more treatment, longer treatment than others. We don't have available capacity. We have only one MRI scan device, okay, and that's it. And the problem is with waiting times and with queues is that the health status of a patient can deteriorate because of long waiting times. Of course, the patient is dissatisfied with the system, and he also or she they can leave the queue because the waiting time was too long. I had a friend, and she was pretty healthy, and one morning she said, "Oh, I don't feel good, I will go to a doctor." And I said, "Okay, call them and ask for an appointment." She said, no, I won't call, I don't want to wait. So she went there and came back after 15 minutes, and they said, what happened? Did they reject? No, they said, I have to wait for 1 hour. And I said, okay, but you have to wait also 1 hour if you have an appointment. So go back. So she was not familiar with our system, okay? And she really thought if she could simply walk in, she could be treated instantly. Okay, naive, but she learned that for later on. Okay, but as I said, they could leave the queue because they don't accept the long waiting times. And congestion could occur in a waiting room. Do you know why congestion is never good in a waiting room? What could be the disadvantages? What could be the problems with having congestion in a waiting room? Now imagine you're coming as an emergency patient and you walk into the emergency department and it's absolutely packed with people. What could be, yeah? Exactly, so we have an increased risk of infection, obviously. So congested areas can become some kind of breeding grounds, right, for infections. So patients with contagious diseases are close to each other, and then we have the risk of a spreading illness. And also resource strain, so hospital resources, staff, equipment, and so on, they may become strained, and this will impact also the efficiency and effectiveness, obviously, of the emergency department. Okay, so queuing theory. Why do we need queuing theory? Often this is used to describe dynamics of how the patients arrive, how they're waiting in a queue, how's the server working. So to describe dynamics and also to analyze waiting times and also to examine the trade-offs between how much capacity do I need and do I expect and try to avoid, for instance, service delays. Okay, so the crucial point here is we are not optimizing things in a mathematical way, at least. Okay, what we are using is the queuing theory for analyzing, for understanding the system better, and then make some kind of improvement suggestion. Okay, but we're not optimizing it in a mathematical sense. And then we can ask different questions: how long is the waiting queue for patients? How long do they have to wait? How is the utilization of the equipment? How many patients can be treated each day? By the way, we made some kind of interviews and they didn't know. So hospitals or emergency department, they don't know how many patients they treat on average, and they don't know how many could be treated. Okay, so which is weird because all the data is there. This is collected. It's simply looking into the data and say, okay, my capacity allows me to treat 20 patients per day or something like this. But if you don't know that, you cannot optimize anything. You cannot improve your processes, obviously. Okay, so and then different questions that can be asked and where queuing theory is very valuable. And this is different to optimization models where we try to minimize the costs. Okay, here we minimize total costs consisting of capacity costs. So, for instance, salaries for physicians, nurses, and so on, and fixed costs, because also the operating room, the emergency room, the waiting room, all of them incur some costs. And then, on the other hand, we have waiting costs. So, again, salaries. For instance, they have to wait. So, again, salaries for the employees. So when doctors are waiting for the results or waiting for an exam room to be cleaned and be ready for the next patient and so on. Okay, and then of course we have patient time. That is some kind of cost. Maybe their health deteriorates because they have to wait. Cost also for losing patients. Then we have some kind of lost profit. Okay, if they don't want to wait in this waiting lines, then they leave and we cannot benefit from them. And the decision variables, what we want to understand is how much capacity shall we have and the processing of the queues. And the parameters, this is what we have to know, is the arrival pattern of patients Are they exponentially distributed, deterministic, whatever? And also how our service durations. I think we talked about it last time, where the hospital didn't know the MRI scan treatment time. And then they had to collect this data to understand how long is, on average at least, the MRI scan. Okay, and if we try to minimize the cost, we have, of course, to understand that there are counter effects. So if we increase the capacity, if we have a second MRI device, if I have a second doctor, a second nurse, then obviously the service cost increase, whereas the waiting times decreases. Okay, so there is some kind of optimum over here, and then although the cost for waiting decreases, here the service cost increases. Okay, so we have to find these overall optimum. Okay, so the question is, how much capacity is needed to minimize all these costs? The problem is that it's really difficult to really quantify the cost of a waiting time. Okay, so how do you quantify that the patient doesn't feel well? Okay, and his or her health status deteriorates. Okay, so the idea is simply waiting time as a policy variable, and the objective is to provide necessary capacity to meet a predefined level. So we say, okay, they shouldn't wait more than, let's say, 3 hours in an emergency department. So how much capacity do I need to fulfill this service level? Of course, we have to consider this trade-off. If we have too much capacity, of course, then we have less waiting times. But at the other hand, we have lower utilization, we have idle times, we have excessive costs, more costs than needed because doctors are sitting around, MRI scans are not used, and so on. If we have not enough capacity, then the utilization is pretty high, so we use the doctors, the capacity pretty effectively, but the problem is that the patients have to wait too long maybe. Okay. And sometimes it's literally too long. Okay, so they used queuing theory to, they used optimization to understand what is optimal, and if they want to ensure that at maximum 5% of the patient, they don't have to wait excessive waiting times, which might be, this is the next question, right? What times are excessive times? Are the 3 hours, 4 hours, 5 hours? So what is acceptable and what is really excessive waiting times? Okay, this has to be defined. In an emergency department, we talk about 4 hours. So if we want to cap that and say, okay, at maximum 5% of the patients can have excessive waiting times, then we need 23% idle time. So 23% of our capacity will be unused. Okay. And this is exactly this trade-off. Okay. 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 Some questions? Okay. Then we need some kind of candles notation of queuing theory, but just a recap. Someone familiar with this notation, A, B, C, and from queuing theory? Okay. Don't worry, we simply remind you of that. So A, so the first notation is the probability distribution of the inter-arrival time, so the time between patients are coming in. The second one, B, is the probability distribution of the service time, so how long this treatment time is taking per patient. And C is the number of servers, the number of doctors, MRI devices, and so on. Okay. Okay, and then we need some kind of classification. So, for instance, D could be the Q discipline, first in, first out, shortest in, shortest out, most urgent one, first in, first out, okay, and so on. And then we have the capacity of the queuing system, which is either bounded or unbounded. So we have particular number of chairs in the waiting room, and more is not, we cannot have more than that. And F is the size of source of input, which also can be bounded or unbounded. And this is simply the number of potential patients simply arriving at the emergency department that could be estimated based on population size, event occurrence, or something like this. However, at least in the case of emergency departments, they must plan for unbounded number of arrivals because of some kind of mass casualty events, natural disaster, whatever. Okay. Inter-arrival and service times, and this is so now we have to fill these A, B, and C, and we have to understand which kind of distribution is most appropriate. So we have, this is the most traditional one, the exponential distribution, capital M. This comes from Markovian process. D is deterministic. For instance, some services are deterministic. For instance, whatever, taking blood tests takes always 5 minutes or something like this. Okay, so that could be assumed deterministic, or this is the highly sophisticated one if we assume a general distribution. So that means here, as an example, the inter-arrival times are exponentially distributed, the service times are exponentially distributed, and we have as service points as a number of MRI devices. Okay, here's some notation. We have the number of servers. Lambda is the arrival rate, so the expected number of arrivals per time unit. It could depend on the number of customers or patients already in the system, but it could also be that it's independent. We have 1 divided by lambda. This is the expected arrival time. Okay, so again, as before, this is the rate. 1 divided by lambda is the time. Okay, interim time. Mean service rate, depending on the number of patients in the system, independent of them. And 1 divided by mu is again the expected service time. And rho, the traffic intensity or service level, is simply the arrival rate divided by the mean service rate. Okay. Okay. And to have it to rho, we assume that also for the later the steady state should be less than 1. That means we should have a smaller lambda than the mean service rate mu. Okay. We will see why this is necessary in a minute. Okay, let's have an example. We have inter-arrival times exponentially distributed, service time is distributed. We have 2 MRI devices, and based on what is given, 42 minutes with for the service time, that means we have a mu, which is 1.429 per hour, and we have inter-arrival rate of 2 patients per hour, which means the arrival time. So every 30 minutes we expect a patients coming in. Okay, and then here we have 0.7 traffic intensity, which is below 1. That's good. Okay, and then we have to differentiate between transient and steady states. So the state is simply the number of patients in the system, nothing fancy. And the transient state is the beginning of the state and the elapsed time. And then when we increase the time frame, then we can say we are at a steady state or at the equilibrium, where the probability to have some kind of a particular number of patients in the system is independent of the initial state or the elapsed time. Okay, and then we need again some kind of notation. P is the probability that exactly n patients are in the system. We have L is the length of the system. Okay, so patients in waiting room and the examination room, so the number of patients in the entire clinic, let's say. LQ, just the number of patients in the queue. So this is the numbers of patients, and W is the time, either in the queue or overall in the system. So the waiting time plus the examination time. Okay, and here we need the steady state in the Little's law. The equilibrium state can be reached if these conditions are fulfilled, and here we see this rho should be less than 1. Otherwise, our Q would simply explode, and we cannot manage it because more patients arrive than we can handle. Okay, and this we never reach equilibrium then. In this case, this is why it's important to have rho that is less than 1. And with little laws, we can determine the length, the number of patients in the system, and also the waiting times in the system. And then we have here more notation. So the overall number of the system is, of course, the number of patients from 0 to infinity multiplied by the probability that exactly n patients are in the system. And with these numbers, we can determine, and due to Little's law, we can determine also the waiting times. Okay, and this can be also used for, or could be modeled using birth and death process, where we simply use a process where entities, or in our case, patients arrive. This is the birth, and leave the system again. This is the death. So this birth represents arrival, death represents leaving the system. Literally, it could be, of course, the death case. And then we have so-called steady state coefficients or equilibrium coefficients, to have 0 patients and to have n patients in the system. Okay, so this is simply initialize the entire process of the, typically in this state of the system where no patients are present, and this reflects the ratio of the product of arrival rates and up to state n-1 and divided by the product of the service rates up to state n. Okay, this is also crucial for our steady state. And then we simply can define the probability of having n patients in the system simply using this coefficients multiplied by the probability of having 0 patients in the system. Okay, so if we know that having the patients overall up to infinity patients is 1, obviously, we can simply replace it by this one. So we have over all these coefficients multiplied by P0. This is 1. So, and if we put that on the other hand, we know what a P0 is, and with this we can determine all the remaining probabilities. So if this is finite, then if rho is finite, then this will be finite, and we reach the steady state. Okay. So the steady state may be at the end. If we, so that doesn't mean that this is deterministic. Okay, so we still have some kind of process, but if you zoom out of the figure, you simply see a straight line, right? If you zoom in, then you see the fluctuation. So a steady state doesn't mean that it's constant or fixed. Okay, it's simply that is in a stable condition, where the fluctuations are surround the mean value. Okay. So for the MMS models, we have some assumptions, and that means, so if rho is, sorry, I need my pointer. So if rho is below 1, then the system converges to equilibrium. Okay, so over time the system will reach a steady state where the number of incoming patients is balanced, okay, by the number of patients being served and leaving the system. Okay, so we have this kind of stable condition. Otherwise, as I said before, otherwise the queue would explode and we couldn't handle it, and we would have this kind of exploding line. Okay, so if we look at this simplified version where we only have one server, one doctor, one MRI scanner, then we can determine the coefficients like this. We can simplify it using this notation, and then we simply can use the geometric series to define the probability of having no patients. So this is here, okay? So because of the geometrics, because this is the geometric series, we can simplify that to 1 divided by 1 minus rho, okay? And then we have the probability of having 0 patients in the system as simply 1 minus rho. Okay, and this can then be used simply to determine the remaining probabilities. Okay. With all these probabilities, we can now determine the number of patients in the entire system, okay? And here we use some tricks. I would like to show you at least one before we finish. So you can see here that pi can be replaced by this one, or also by this one. So replace pi by this notation, and you can see here that rho is independent of I. We can put it out of the sum, and we can use also 1r rho out of the system, out of the sum, sorry, and we have rho up to I minus 1. And this is nothing else than the first derivative, which is again independent of I. This can also be used and put out of the sum. And then this is simply again a geometric series, and then we end up with a very simple formula. So the number of patients in the entire system is simply lambda divided by mu minus lambda, okay? Which is pretty elegant. And then a very similar approach if you want to know the number of patients only in the queue. And with these, we can, so with LQ and L, with these numbers, we can also easily determine the waiting time for the patients in the entire system, and also for the only for the queue. Okay. If you have more than one server, you can try to find out how this is derived, but I will skip that. Obviously, just that we have to differentiate if we have less patients in the system than servers. This is different than having more patients than servers. Okay, then we have slightly different notation here, and we have to differentiate between these two cases. Okay, I will skip that too. And we'll finish with an example. So the question is now how would the waiting time and the length of stay in the system change if a second nurse could also take a blood test, not only one, okay? And if you see that we have this lambda and mu given from the text, using this formula, then we have this particular example following. So first of all, you see the traffic intensity decreases significantly from one nurse to another one. The probability that no patient is in the system is higher, obviously, because idle times are increasing. But what is more important is the length, the queue length. So how many patients are waiting in the queue. This is more than one if only one nurse is present, and less than one if two nurses are there. That means no one, so for the second, no one is waiting in the room, okay? So how many numbers of patients are in the system? Obviously, if we have one nurse is one patient's waiting, one patient is treated. In the case of two servers, two nurses, we see that only one is present in the treatment, and almost no one is waiting, okay? And here the same, if we have only one nurse, 4 minutes they have to wait, and 2 minutes is treating time. So overall, 6 minutes the patient has to wait. In the case of where we have two nurses, we can significantly decrease that. That means the overall time the patient is spending in the system depends only on the treatment time, and almost no waiting time. Okay, so the patient can instantly go into the treatment, and the nurse can instantly take the blood result. And what I just want to mention is that you can use these theories, this queuing theory, to analyze the system and to understand if I increase my capacity, I could improve the waiting times, improve the system utilization also. Okay, so that doesn't need to mean that S2 is optimal. Okay, this is another point. But with the second nurse, we see that there's an improvement here. And okay, I will stop here, obviously. So the last one I will skip, so that means this is also not, if you're interested, of course, you can have a look on the slides, but it won't be part of the exam. Okay, I will skip that, and we will start next time with patient transportation. Okay, so thank you for your attention, and see you next Monday or Tuesday. Bye, guys.